Hi, everybody, and welcome back. Today we're going to do 4.2.2. Which tool should I use? We will be choosing between sine, cosine, tan, and the Pythagorean theorem. But that's not the star. The star is sine, cosine, and tan. So today we're going to just devote our time to developing strategies that we can be able to rely on throughout the rest of the course. We have several tools that we can use to help solve for the length of a side of a right triangle when given an acute angle and any side length. And the question that we're trying to answer today is, how do we know which tool to use? And how can we identify the relationships between the sides and the angles? Okay, learning goal. I'm going to write it in first person. I will be able to choose between sine, cosine, and tangent to solve for a side length of a right triangle when given an acute reference angle and the length of one of the sides, period. Okay, let's get going. Problem 4-68. The first instruction is look through all of the triangles and see if they look familiar. If possible, determine the missing side lengths without using a trig tool. Next instruction, identify which tool we should use based on where the reference angle is located and which side lengths are involved. Next, write and solve an equation to determine the missing side length. So I'm going to start with number 1. Look through all the triangles and see if they look familiar. If possible, determine the missing side lengths without using a trig tool. Okay. First triangle, 28 degrees, nothing special, nothing familiar about it. Next triangle, 45 degrees. Okay. This one I've got. I know that this is a 45-degree angle, 45, 45, 90 triangle, just based on the fact that right triangles with a 45-degree angle are isosceles. I can say, hey, if this side length is 8, which is given, x must also be 8. X equals 8 because this is a 45-degree right triangle and is therefore isosceles, meaning the legs of the triangle each have the same length. Okay, let's see. 61-degree angle, 25, 60, 30. 60 and 30 are special, but we'll learn more about those later in the course. Okay, 0-degree angle. Well, if I picture it, as the angle increases, I move from 0, here's 0 degrees, all the way up to, I guess, 90. 0-degree angle cannot lift off the page. There can be no length here. X must be 0. 0 degrees tells me that the tan of the angle is 0. But I don't even need that. I know that if I have no lift, I have no rise. X can only be 0. Okay, next 73-degree angle, 42-degree angle. For the rest of these, I'm going to have to use trig tools. Okay. So for this one, I'm going to identify which tool I should use based on where the reference angle is located and which side lengths are involved. Okay. Pardon me, I'm gonna pause for a second. Okay, back at it. So for this one, I've got 28 degrees with, let's label opposite and adjacent and hypotenuse. Okay, so since I have a triangle that deals with the opposite length and the hypotenuse and an angle, I'm going to use sine. So I have sine of the angle, 28 degrees, equals opposite over hypotenuse, x over 19. And then I'm going to do cross multiply and divide. So I have x times 1, which is just x, equals 19 times sine of 28. And if I put that into my calculator, I'm good to go. X is about equal to 8.9200. 4 digits for trig after the 0. Okay, next one is done. Part C. This deals with, okay, well, across from the angle is the opposite side. So this must be the adjacent, and this is the hypotenuse. Hypotenuse is the longest, adjacent is the leg that is not opposite. So since I'm dealing with adjacent and hypotenuse, I have to use cosine. So this is cosine of 61 degrees is equal to adjacent over hypotenuse, so 18 over x. I cross multiply, and I have x is equal to cosine. Oh, sorry, I misspoke. X times cosine of 61 degrees is equal to 18 times 1, which is just 18. And x is not alone yet, so I need to divide both sides by cosine of 61 to get there. And that's what I'm going to put in my calculator, 18 over cosine of 61. And when I put that in my calculator, I get that x is about equal to 37.1280. Okay, next problem. So again, I need to figure out what parts of the triangle I'm working with. I go across from 25 degrees to find which side is opposite, and that's side with a 6. My longest side is always my hypotenuse. And my adjacent side is right here. Now, since I'm dealing with my hypotenuse and my opposite side, because I want my hypotenuse, it's got the x there, and my opposite side is given, I'm going to be using sine. So sine of my angle, which is 25 degrees, is equal to opposite, which is 6, over hypotenuse, which is x. I cross multiply, I get x times sine of 25 degrees is equal to 6 times 1, which is just 6. X is not alone yet, so I need to divide both sides by sine 25 degrees. And I get x is equal to 6 over sine of 25 degrees. Put that in my calculator, and I get that x is about equal to 14.1972. Pardon me, the cat is chewing on my... Anyway, I continue. Part E. I have a 60-degree angle, nothing on my opposite side. My adjacent side is 8, and my hypotenuse, the longest side, is x. So I have cosine of 60 degrees is equal to 8 over x. I cross multiply. 1 times 8 is 8, which is equal to x times cosine of 60. X is not alone yet, so I need to divide both sides by cosine of 60. On the right-hand side, it cancels, and on the left-hand side, I have 8 over cosine of 60. I put 8 over cosine of 60 into my calculator, and I get that x is about equal to 16 point, honestly, you can just write 16. But if you're stuck needing 4 digits, you could write 0.0000. It would be better to rush write 16 though. Cosine of 60 is exactly 1/2. So 8 divided by 1/2 is 16. Anyway, for trig, we traditionally use 4 digits after 0 after the decimal. And that's why I'm doing that. Because for those of you who take calculus, which is, oh, wait, all of you are going to take calculus. Very, very good. Anyway, for those of you who take calculus, it's important to know that 4 digits after the decimal for trig functions. Anyway, next triangle. I label my opposite. The side across from 30 degrees is the opposite. I label my adjacent. It's the one that's neither the opposite or the hypotenuse. Hypotenuse is the longest side. Okay, so since I'm dealing with opposite and hypotenuse, I'll be doing sine. Sine of my angle, which is 30 degrees, is equal to the opposite over the hypotenuse, so x over 42. I cross multiply, I have 42 times sine of 30 degrees is equal to x. And I put that in my calculator to get that x is approximately 21. Actually, x is equal exactly to 21 because, again, we have a situation where our trig function returns an exact value. Anyway, you could write 21.0000. I don't want to, so I'm not going to. Okay, next problem. I see a cute cat. See if Mummy comes. Mummy! Not happening. Anyway, next problem. We've already done G. Now we'll do H. I go across from 73 degrees to label my opposite side. There's nothing there. Adjacent to 73 degrees is X. And the hypotenuse is the longest side. Since I'm dealing with my adjacent and hypotenuse, I'll be using cosine. Cosine of 73 degrees is equal to x over 3. I cross multiply. I have 3 times cosine of 73 degrees is equal to x. Ah, there's the cat. Go away, Bubby. I put that in my calculator and I get that x is equal to 0.8771. And you might think, hey, that's a small value. And you're right. It is. But I mean, 73 degrees is kind of steep. It's getting close to 90. And how far do I have to go over to get up enough to make my hypotenuse 3? Not very far, less than 1. Okay, last one, part I, and then we'll turn to the next page. All right, part I have 42 degrees. Across from that is the opposite side, which is X. The longest side is the hypotenuse, and adjacent to 42 is 12. Since I'm dealing with my opposite and adjacent side, I'll be using tangent. Tan of 42 degrees is X over 12, opposite over adjacent. Now, 42 is almost 45, so I'm thinking X is going to be pretty close to 12, maybe like 11-ish, because it's a little bit less than 45 degrees, but let's find out. I cross multiply, I have 12 times tan of 42 is equal to X times 1, which is just X. I put that in my calculator, and X is equal to 10.8048. Aha. Close. Next page when you're ready, everybody. Bada bing, bada bing, bada, whoa, boom. All right. Now for this next page, Let's hear about Marta. Marta arrives for her math test, only to find that she has forgotten her calculator. She decides to complete as much of each problem as she can. So in the first problem on the test, Marta has to solve for the length x in the triangle shown below. That's a typo. It's right here. Using her algebra skills, she writes and solves an equation. Her work is shown below. That's also a typo. I'll fix that after. Explain what she did in each step. Okay, so for step 1, she wrote sine of 25 is equal to 29 over x. That's opposite. And hypotenuse. So she just set up her equation. She wrote an equation. Step 2, looks like she started to cross multiply and divide. She cross multiplied. And for step 3, it looks like she didn't have x alone yet, so she divided both sides by sine 25. She divided both sides of her equation by sine of 25 degrees to isolate x. Problems like this, where you observe the process, are really important because now we actually have steps that we can use to solve any of these problems. What Marta did was perfect. All right, part B and part B. Marta's answer in part A is called an exact answer. Let's use our calculator to help Marta determine the approximate value of x. Anytime you have an answer that uses no rounding, it's exact. When we put this in our calculator, we'll get an approximate answer because we'll need to round to the 4th digit. The rounding is what makes our answer approximate. Anyway, so I enter 29 times sine of 25 on my calculator. And we get that x is approximately equal to 68.6198. Exact and approximate answers, everybody, have different usefulness, different uses. I would not know where to put my exact number on a number line. But 68.6198, I can graph that. I can plot that. I can say it's somewhere between 68 and 69, a little closer to 69. I can picture that size. Oh, this is an error. Sorry, everybody. I shouldn't have written 29 times sine, 29 divided by sine. Sorry. Anyway, hopefully that answer is correct. I'll enter it in a calculator. I'm not sure. Let's see. 29 divided by sine of 25. Okay. So the answer is correct. Just what I wrote was wrong. This should have been 29 divided by sine of 25. Sorry, I'll fix my answer key too. All right. What is the difference? This question asks. The next part. What is the difference between an exact and approximate answer? So approximate answers are rounded. Exact answers have no rounding. Exact answers are really useful because they give perfect numbers. With all of the information intact. But they're not so easy for our human brains to work with because it's harder for us to know where they belong in the order of numbers. So rounded answers are nice for us because we can picture where to put them on a number line. Okay, part C. Marta's teammate Ziv said he solved it differently, but still got the same answer. He started with the equation below. Explain why this equation has to give the exact same answer as in part A. All right, so what I noticed right away is that Ziv is using a different angle. Let's see why that can make sense. It must be this angle. How could we know that that's 65? Well, I know that the angles in a triangle add up to 180. So I'm going to do 180 minus 25 minus 90, and that does equal 65. So what Ziv did was Ziv used a different reference angle for the same triangle. Because he used, I don't know why I'm assuming, oh, Ziv is a boy, okay. Because he used a different reference angle, the adjacent and opposite labels switched. What I mean by that is the side which is opposite the angle 65 would be adjacent to the angle 25. The side which is adjacent to the angle 65 would be opposite of the angle 25. They switch. And since they switch, the trig function, which you would use, also switches. So cosine of 65 should be adjacent over hypotenuse, which would in this case be 29 over x. That has to be the same thing as cosine of 25 because that would also be 29 over x. Just to see that a little bit bigger, we're going to do another example, part D. Solve for y in the diagram below in two ways using both sine and cosine ratios. Make sure both strategies result in the exact same answer. All right, so using sine, we have the opposite and the hypotenuse. Sine of 53 should be opposite, which is y, over hypotenuse, which is 5. I cross multiply. 5 times sine of 53 equals y times 1, which is just y. I enter that in my calculator, and I get that y is approximately 3.9932. Now, if I want to use cosine, let me draw the triangles separately. So here's 53, y, and 5. When I'm looking at the angle 53, y is opposite, and 5 is hypotenuse. If I want to use cosine, I'll have to figure out what that missing angle is. This angle will equal 180 minus 53 minus 90, which I've already done this. I don't do it in my head. I know the answer is 37. If I want to use this angle, 37, I'll redraw the triangle just to make things hopefully really clear. I still have y and 5, but now I'm going to use cosine because now y is adjacent since I'm talking about a different angle. So cosine of 37 is equal to y over 5. Again, I cross multiply. 5 times cosine of 37 is equal to y. And so y must be 3.993. 2. This relationship where you can switch trig functions by switching angles is one that we're going to define more formally in just a moment. Notice I did in fact get the same answer. And I should. I'm dealing with the same triangle. We want math to be reliable, logically consistent. Okay, so now let's just formally explain that relationship. Explain and use the relationship between the sine and cosine of complementary angles. So just as a review, complementary angles are angles which add to 90. And if you haven't noticed yet, the acute angles of any right triangle, let's just name these theta and beta. The acute angles in right triangles are complementary. So in this example, theta plus beta equals 90. Okay, so formally, what we can say is that sine of theta equals cosine of beta if zeta plus beta equals 90. Example, sine of 30 equals cosine of 60, since 30 plus 60 equals 90. Another example, sine of 2x equals cosine of whatever, I can make it anything. 7x if 2x plus 7x equals 90. In this situation, x would be 10 if x equals 10, because 9x equals 90 means that x is 10. And that is just because if I use the other angle in a right triangle, then what was the opposite becomes the adjacent, and what was the adjacent becomes the opposite. Okay, last problem, 4-70. In problem 4-68, we used trigonometric tools to solve for a side length. But do we have a way to determine an angle measure? This is a preview of our next lesson, by the way. Okay, we examine the triangles below. Do any of them look familiar? How can we use information about the side lengths to help figure out the reference angles? Okay. We may be using our trig table graphic organizer from chapter 3. But spoiler, we're actually not going to do that because I don't have it with me. So let's just go with this. Okay, this is isosceles. So I know the angle has to be, it's an isosceles right triangle. So I know this angle is 45 degrees. I also know that tan of 45 is equal to 1 because this is a familiar triangle that we've done many times. 9/9 equals 1. The angle must be 45 degrees, period. Okay, next problem. Well, I don't know exactly what this is going to be, but I know that tan of 1/5, tan of my angle is equal to 1/5, which is 0.2. I'm going to put a pin in this one because I think I'm going to have to use trial and error. Okay, this one. This is, I've got, here's opposite, here's adjacent, here's hypotenuse. Cosine deals with adjacent and hypotenuse. So cosine of the angle is about 5/10, which is 0.5. Now this angle has been in the notes many times today, so you may just find it on your own, but let's say you don't. I'm going to use trial and error. I'm unstoppable because I'm willing to use trial and error. Okay. I'm going to press pause. I'm going to go grab my calculator and then I'll be right back to do trial and error. Okay, so trial and error. Let's see. Tan of what is 0.2? Let's try tan of 30. Tan. I'll change my brightness. Does that help? I don't know if it's going to be very clear, but anyway, I'll try. Tan of 30 is 0.6. So 30, too big. Okay, let's try tan of 10. Tan of 10. That's getting closer. It's just a little bit too small. Okay, I'll try tan of 15. That's too big. Okay. Tan of 11. Pretty close. 0.1943. Let's do tan of 12. 12, 0.2125. Let's do 11.5. Pretty close. 11.5.2034. Let's do 11 point. It's a little too big, so let's do 11.4. 21. Let's do 11.3. 1998. Let's do 11.35. Ooh, that's so close. Just a teeny bit too big. Let's do 11.34. Very close. 3.3. Very close. 3.2. Very close. 3.1. Oh my gosh, look how good that is. All right, I'm doing it. I'm going to say theta equals 11.31. That's good to 5 decimal places. And in trig, you only need 4. To be clear, you need 4 for this. So this would be 0.2000. Okay. I'm feeling pretty good about that. Next class, we'll have a more direct way to do these problems. But for now, all we know is trial and error. So we're doing it. I'm not above any method. Okay, I need cosine of theta to be 1/2. I'll try 45 degrees. Cosine of 45. That's 0.7, too big. 45, too big. I'll try 25. Cosine, oops, press clear. Cosine of 25. Too small, that's about 1. Wait, too small. That's still too big. Was cosine of 45 really too big? Trying to get to 0.5. Hold on. Cosine of 45. Too big. Cosine of 25. Even bigger? Make a number line. Cosine of 10.9. Cosine of 20. 0.9. Cosine of 40. 0.76. Cosine of 50. 0.64. Cosine of 60.5. Okay, I know it's 60 because that's 0.5, but that was a window into my mind. This is how I think. If I don't know what's going to happen, I want to investigate. This is kind of an interesting relationship to me. I'm tempted to graph it, but for now, let me say cosine of theta equals 0.5 tells me that theta is 60 degrees. I'm going to graph this. Okay, the lesson stops here. You're done. But if you would like to stay while I do my little graph, please do, because I think this is interesting. Okay, so I'll put my angle here and my y here. So I'll make x my angle. So when my angle is 10, y is about 1. When my angle is 20, y is still about 1. When my angle is 30, I didn't do. 40, I'm down to about 7 something. 50, I'm getting close to a half. 60, I'm at 1/2. What does this look like? What about when I'm at 0? What's cosine of 0? 1 exactly? Whoa, okay. And what's cosine of 30? Oh, that's 3.86 though, so it's about right here. Smooth curve. Is it going to go all the way to 0? That's an interesting graph. Well, I don't know, but this is an experiment I'd like to continue. Anyway, our lesson ended here. We found the angle. I hope you all have just a beautiful day, and I will see you next time.